All righty. Well, thank you everybody for joining us today. I have really been enjoying these meetings. I think we've had a lot of good presentations, and I'm sure that the presentations today will live up to the presentations of all the ones that have already happened. Looking forward to having a presentation from Bob here with PPRP, and then we're going to be talking about the life cycle assessments from NREL. And then we have a study update from Kathleen and Bradley and Shreyas. So really looking forward to hearing more. Gavin, I'm glad you got your microphone working so that we can enjoy your presentation. Hopefully we can take care of that background noise too. Good luck. Bradley, do you want to kick us off with some roll call?
Yeah. So I'm going to go through the members. So Senator Benjamin Brooks.
Here.
Delegate Mike Rogers. Tyler Abbott.
Yep.
Evie Schwartz.
Here.
Josh Kurtz. David Chai. Diana Mendez, or is it that Menendez? Pearl Donahue Valet. David Bugelman. Stacy Ono.
Here.
And Scott Elias.
Here.
All right.
Cool.
Maybe we'll start sending out Friday afternoon emails to remind some folks to join us here. Right. Thanks, Garvin. If we need to swap up presentations, we can do that too. But Bradley, do you want to? I guess I can kick us off. Bob, you can take it away with your presentation.
Can you all see that?
Yes. Well, we can see your calendar.
My calendar? Oh, oh, to see how busy I am. Sorry.
Exactly. For redoing work.
Go to Plan B, put it on the other screen.
All right, we got the right one now.
There we go. How's that look?
Looks good.
Looks good.
Okay. So PPRP has put together this decommissioning report. So I'll go into details what we do here briefly throughout the presentation. But as we do this, just kind of let you know. So again, I'm Bob. I'm the director of the Power Plant Research Program located within DNR. So again, you all know what decommissioning is. I mean, we're here to discuss it. We've been reading about it. And this is a 3-year study. I mean, it's really kind of a literature-based. And we also looked at the projects that we do. So we do the environmental and socioeconomic impact analysis for CPCNs, in particular solar, but I'll go into details in a minute here. And again, we've looked at to date about 82 projects, maybe a few more than that since I put this together because we're moving rather rapidly through the process. Again, what we do, we do a coordinated 7-agency comprehensive objective assessment of the environmental and socioeconomic impact analysis for CPCN cases. Right now, we have a lot of solar cases. You'll see that in a minute here. And we also look at transmission cases, but that's a dirty word. We won't talk about that right now. But we make recommended licensing conditions of the Public Service Commission. That's pretty important. So they have the authority. I want to make that pretty clear. So, and we look at about 70 different factors in all of these cases. And then we generally assume a 30-year lifespan for these projects. So what we see, we've been doing solar projects probably since 2011 when I first came to PPRP. I think I have one of the first cases over in Kent County. So when you can see the numbers, these are number of cases. So you'll see the gray is the solar cases, the yellow is transmission. That's pretty much all we've seen. We don't really do much hydro work in the state, although that would fall into us. We have done some wind cases during this time period. But again, I mean, we're kind of looking at solar. And then I did projections. I took out my crystal ball and I said, what do we see in the future? You can see that big increase at the end in 2024. Currently, we have 19 solar cases. But again, these are the community solar cases. They are generally small projects, what we consider small projects, but still fall within the CPCN. They're within a 2 to 5 megawatt range, covering between 10 and 25 to 30 acres of solar panels. Based on what we see in the future, we suspect this to continue and only increase. But again, it's kind of a PJM is to blame here too. We assume PJM is going to let up a little bit and start seeing more cases. And I talked to PJM 2 weeks ago, and they said they're coming. And so we're still waiting for these large projects. We have 2 larger projects right now, 50 megawatts and more. We have a few in pre-application. We have a 222 megawatt project out in Allegheny County that is in pre-application with us. So that's probably the largest project in the state that we will be seeing probably in the winter time-ish. But again, this is kind of predicting out for the next couple of years what we will see. So again, I pirated this from a different report. We call it CEIR. It's a cumulative environmental impact report. This is available on our website. Again, if you go to Google search and just type in Maryland PPRP, you'll see on the right-hand side CEIR, or I think it spells out Cumulative Environmental Impact Report. So buried in there in that 300+ page report is this table right here, which looks at solar removal panels over the years. This is the number of panels, and this is based on what the applicant tells us is the life of the project. So they generally say between 25 and 35 years. So we took our spreadsheet, we estimated number of panels that will be decommissioned through the years. And this is current projects. So this is the projects we know of. This number is only going to increase significantly as we see more and more solar going on. So again, we do recommended license conditions, and we do look at decommissioning. That's one of these sciences that has been dynamic and ongoing and consistently changing in the 14 years we've been doing solar siting. We have learned a lot. Actually, we've learned through our mistakes what should be included. And I have some examples here coming. Again, it's just to show you what is included with our using acronyms in my head, RLC, recommended license condition. But again, we look at the cost. We always ask for a 5-year update. So we make that recommendation to the Public Service Commission. So every 5 years, they have to back and review their decommissioning plan and resubmit it for approval by the Public Service Commission. And generally, we also define what it is, but I'll go through that in a second here. So here's an exact example of what a decommissioning condition would look at. You see it has the amount in there. I kind of highlighted the important part in there. Again, this is all public information. If you just want to go on the Public Service Commission website, or you let me know, I can send you the link. It's a little difficult to find if you haven't been there before, but you basically just put in the name of the case and it'll pop right up, or if you know the docket number, that's even easier. But again, for this particular case, it's a smaller project. I think it was less than 5 megawatts again, but they have to post a financial bond in the amount of $577,000. That's what we call the decommissioning bond. Here again, that could be held by either the county or the Public Service Commission. It really depends. The state prefers the county to hold them, and generally, recently, the county does hold those bonds. But again, this is just part A of decommissioning. So this is looking at the amount. And again, it says every 5 years it needs to be updated. And during that process, it goes before an admin hearing for the Public Service Commission, where we, PPRP, will take a deep dive into reviewing that report and actually making changes. We do the math with them make sure their math makes sense as far as the bond. We also looked at recommending reuse and recycling. We don't mandate it at this point, but we certainly, in their decommissioning plan that's received from the applicants, there is a third party that has agreed to purchase those panels at a certain price. But again, they do incorporate salvage value into their decommissioning costs. We have worked out that they cannot exceed 85% of the documented, and that's important because a third party has agreed to pay X amount for that salvage. We can't say it can't exceed 85%. Again, there's a trigger. So this is what we kind of struggle with too, is when do we say decommissioning should occur? Again, we've never had a decommissioning plant in Maryland that has gone through the process. But again, we have defined it currently as not generating electricity for sale. So that's how we define it. It's a pretty distinct line when they export for sale. But again, we've not seen that yet. Again, you all have been familiar with these presentations. I reviewed them over the weekend and saw that you guys basically EU has been doing a lot more work than we certainly have. We are catching up, and it is required in European Union. Sorry, I work in a land of acronyms. Again, we are making excellent progress in the U.S., but we are still lagging a little bit behind. And of course, you know, some, especially the older panels, do have some hazardous materials in them. So, and this is just a picture of a farmer friend of mine who has solar next to his chicken houses that he used to completely power his chicken houses. So yesterday, just to give you a little treat, I said, now what's important to us? So I said, what's in the future? So I just did this review yesterday after attending Mako. So the math may not be exactly, but I think it's extremely close, if not. But we still need to add about 5,000 megawatts of solar generation. This is all types of solar to meet the current RPS. So I converted that to about 25 million panels. And currently we have about just over 1,500, closer to 1,600 megawatts of installed. This is utility scale solar. This does not include those small projects that don't require CPCN, including rooftop and some of the smaller community solar projects. So as far as decommissioning, again, when we look at decommissioning, there's a whole lot more than solar panels. We struggle with removing all components. This came up probably just before COVID, like 3.5, 4 years ago. Some of the decommissioning plans were leaving all the infrastructure that couldn't be seen, basically all the underground wiring. They were saying, oh, we're just going to leave it, or the pilings, they were saying, we're going to cut those off. And finally, we kind of talked to some folks and said, that doesn't make any sense at all to us. I mean, if they want this to go back to farmland, they need to remove all components. And that's what is currently we recommend to the Public Service Commission, and the applicants have agreed to that. We also talked about reestablishing ground cover. The vegetative buffer, we just had a conversation about a week ago about vegetative buffer, whether it would be moved or not, including the access roads and the stones. They generally put down stones in these fields to give them access and lay down areas. But again, this really depends on the current landowner and what their plans have for the property. And again, we've not seen land lease agreements between the current owner of the land and the applicant. And when we do see those, they're so redacted, they don't make any sense anyway. So decommissioning costs, this has been all over the place. We kind of struggle with this. You'll see in the next slide some of the estimates. We've kind of narrowed it down, we've done studies, that's what kind of looked at studies over the years and what's normal, what should it cost per acre, and it is not consistent at all in Maryland, again. So we've looked at prices. Again, we've looked at about 70 decommissioning plans for solar in Maryland. The range for those has varied anywhere from $0 to $95,000 per acre. Yeah, the zero, because they included 100% salvage value. They had someone purchasing panels at 15 or 18, or actually I think it was $22 each. So basically, they said they didn't have to post a bond because there was enough value in the current panels and the salvage value. So we argued that pretty fervently, and I think we pretty much said that doesn't make any sense to us. So, and I think the Public Service Commission has agreed, especially lately in our assessments of decommissioning costs. But of course, there is that recycling that can occur, and of course, like I said, 85% of that, as far as salvage value, can reduce the cost of the bond. And currently, which is a new thing that just happened probably in the last two cases, solar cases we've had, is now the decommissioning plans are actually incorporated into the application. This is probably no big deal for you all, but it certainly does help PPRP, because otherwise we have to review it in a separate through a separate admin hearing, and it costs us a significant amount of time and money. So with that said, we kind of looked at some of the costs. And this is a multi-state, so this is just not Maryland. This is looking at different states over time and what it costs. Again, costs are all over the place, ranging. And I think this is, cost per megawatt hour. Cost per megawatt. So again, it does vary significantly over time. And again, this is in the report that we can certainly make available to you all as a PDF. So I'm sure that question will come up. Again, nothing's been decommissioned as far as solar in Maryland at this point. Our oldest site is on a prison in Western Maryland that's about 15 years old. Again, we talked about decommissioning bonds, and also, and this is really not a static process at all. We continue to learn. Just going through this report, we took a deep dive on what other states are doing, what we're doing, and again, it's a process that we have learned a lot from over the few years we've been doing solar decommissioning plans and reviewing those. And also looked at modules throughout the U.S. and kind of looked at it's a pretty early process that we have here in the States. But again, currently a lot of them do go to landfills. In fact, I visited a solar site in Anne Arundel County, and they had a stack of solar panels there. And they're only been in operation about 5 years. And I was like, well, why do you keep solar panels? I mean, it had to be 40 panels sitting on site. And they said, because some of these they're broken. There's errors. I mean, they're still under warranty, so they send them back to the manufacturer. So again, some of these are actually being so-called decommissioned now and being replaced by new panels. So, again, and we'll see these changes in time. That's why salvage value certainly will change over time. We looked at that years ago. Oh, is there a question? Again, I'll make the report available to y'all. And I always like to throw this picture at the end. The solar panels have been around. I think this is 1954 solar panel. But with that, again, I will make our report, convert that to a PDF for y'all and pass it through to Bradley. Are there any questions?
Yeah, we had two questions in the chat. The first one's from Andrew K. So for the removal slide, I presume that this does not include home roof installs or other projects that would go through TTCN.
I'm sorry, say it again. You're breaking up a little bit.
Yeah, for the removal slide, there was just a clarification requested that it doesn't include home roof installs.
Correct. Yeah, it does not include home roof. Yeah.
And then I had a question, like how often for the bonds that folks are getting, how often do they have to recertify those?
Yeah. So, I'm sorry.
Go ahead.
Yeah, so every 5 years, they have to come back before the Public Service Commission during an administrative hearing and resubmit the decommissioning plan. And part of that is they have to update that bond. So we think the bond's actually going to increase over time as the value of the panels decreases because they're getting older and less efficient.
Oh, interesting. Okay.
Yeah. Yeah, I can't see the questions. I'm sorry, and I can't see the chat.
No, it's quite all right. We also had another question from someone in the audience, and then David Comas, I think you're after that. Is that Rayo?
This is Garvin Heath from the National Renewable Energy Lab. I'm sorry, I joined by phone for a moment. Hopefully I can switch to the computer. Can you hear me?
Yes. Yeah, we hear you.
One thing that I wanted to let the speaker and others from Maryland know is that the National Renewable Energy Laboratory, in collaboration with the Electric Power Research Institute, will, in the next 2 years, complete a what we hope to be a tool of record for calculating standardized decommissioning costs that may be valuable in the context of the discussion that we're having and for the state of Maryland. So I wanted to let you all know that. And if you'd like to participate in either testing or just learning more about our plans for that, and maybe even participating in that 2-year process of its development, you can certainly let me know.
Yeah, thanks. Sign me up. That'd be great. Yeah, love to beta test it.
Okay, fantastic. Please, it'd be great to get an email from you because I'm not sure I have your contact information. And yeah, then we'll be in touch on it.
Okay, I'll put it into the chat in case some other people have questions. They want to email me directly also. Yeah.
All right, there was a question from David Comitz.
Just a comment. Bob, I had also asked some solar developers why there were extra panels just sitting around the field. And their comment back to me was that if a panel goes bad on the system, we may not be able to go get a matching panel because they may have been discontinued. So we keep some extra panels on the field so that we have a match that can go in when a panel fails.
Yeah, that's a great comment, David. Yeah, I didn't think about that. Yeah, because you're right. It's got to be very similar. Like the plugs and everything have to be the same. So, yeah.
All right. So if there are no other questions, we can probably go to our next speaker, Garvin, although I think he just jumped off and is trying to get back on. These presentations will be on our website as well. And so will the recordings. Do we have Garvin back on? And if not, we can probably move on to the university. But Evie, it looked like you had a question.
Sorry, one more question for Bob. About the definition. Did I read correctly that it's defined as end of life only 12 months after there's zero electricity for sale?
Yeah.
Why is that the definition? Isn't it likely that panels will keep producing for much, much longer and might be producing at very little? But how did you come up with that definition?
Good question, Evie. I don't know. No, I'm just kidding. So what we did, we worked with developers and said, what's reasonable? So, because a lot of them are like, well, we know when we get to the end, what if there's a significant issue, like a storm that knocks it out for a certain period of time? They won't be putting electrons on the grid at all. Maybe they said maybe up to several months. So again, we want them to produce. So we don't want to make it so difficult that they're not putting electrons onto the grid. So we kind of worked with them and said a year seems reasonable. But again, we used to have, I think it was 3 months or 2 months, really tight. And they said, again, we kind of worked with them and came up with a year. But yeah, again, it's evolving science, so and technology. So yeah, I'm more than willing to talk about that off the record too, Abby. But thanks for the question.
And it looks like there was a comment in the chat from Scott Elias. Different states and counties have different definitions. Some states say 1 year, some say 18 months.
And I'll just chime in just to clarify also, because sometimes it has to do with the definition of when they're quote unquote abandoned or when they're quote unquote, sort of legally obligated to be decommissioned. The way I would think about it is similar to how there's a construction cycle that doesn't happen immediately for being able to bring, projects online that takes, a long time. The actual decommissioning process could take a long time as well. So I just wanted to clarify that because we see in different jurisdictions, sometimes, it says 12 months, sometimes it says 18 months. Et cetera.
Okay. If there are no other questions, I think we can probably move on to Garvin Heath to talk about life cycle assessments. Garvin, is everything working for you? You sent our presentation to us beforehand. I can present it if that helps.
Okay, how about that? Can you hear me now?
Yes, yes, we're all good.
Okay, super. Yeah, let me get the presentation up and then hopefully I can share. Sorry, Google doesn't work very well with with at least PC computers that I have and in our security, so it's always been a bit of a challenge. And I'm going to. Okay, can you see the slide?
Yeah, we're all good.
Super, thank you. Okay, this is Garvin Heath from National Renewable Energy Laboratory. I can put my face on now too. I'm at the airport, and I would told you all in advance I would be. So apologies that there is that, and hopefully there's not too much background noise. But I would asked to present on life cycle assessment as well as on circular economy for solar photovoltaics. The National Renewable Energy Laboratory has done a lot of research in this area. I will try to put in the chat, maybe during questions, a link to a website where we have almost all, not the most recent, but almost all of our publications. I also am the manager of an International Energy Agency task force of international experts called PV Sustainability, where we also deal with both life cycle assessment and circular economy. So I'm going to share some, I think, relevant results from both of those. Just to give you a little background on NREL, we're in the center in Colorado in the blue diamonds. It's I started 16 years ago, and we've more than doubled, almost tripled in size. And we do research in a lot of different areas, and renewable energy, like photovoltaics, is one of them. We have partnerships with state and local governments. You can see that on the left. As part of our portfolio of who we partner with, our biggest partner is Department of Energy. We're a Department of Energy national lab, but we do a lot of other work for many others. And so these are just the areas that we work in broad buckets, and in particular, solar is the topic here. So I mentioned the International Energy Agency. This is a program. There's a program within it called the Technology Collaboration Program. Within that, there's one that's been focused on PV for around 30 years or so. And I lead a task within that on sustainability. You can see the topics of sustainability are circular economy, life cycle assessment, ecosystem integrated PV, and then other topics. So I wanted to start with a definition of what the life cycle is. This is a field of expertise for myself and as well as others at NREL and the PVPS Task 12 group. All technologies go through the life cycle. Some of them, combustion technologies, will have fuel, and the fuel has its own life cycle, something we call the fuel cycle. And then that sort of is inserted, if you will, into the combustion phase. But the main four stages, or three really, are the upstream. We call it the upstream. That's where we get the resources and we do the component manufacturing and then the construction on site. Then there's the operation phase, including maintenance, would also include a fuel cycle if there is a fuel involved. And anything having to do with the end of life of that fuel also is in the operation phase. And then the downstream for the physical plant is where the decommissioning and recycling occurs, as well as any disposal that would occur. Life cycle assessment has been practiced for over 40 years, and it has methods that are codified in standards and guidelines, and I'll talk to you about some specific PV-related life cycle assessment standards. This is a project that I led basically when I first started at NREL. We've been continuing to refine it ever since. We've done a systematic review of all published life cycle assessments for electricity generation technologies. Not all of them have been completed in recent years because we rely on funding to do these updates, and some of it is more targeted. But I am confident in saying that the results haven't changed too much from what, especially in these broad comparisons across technologies that you see here. This was first published in an IPCC report, Intergovernmental Panel on Climate Change, and we've maintained it ever since. So on the right-hand side are the non-renewable resources, including renewable energy. On the left-hand side are the renewable energy resources to produce electricity, and in the middle are storage technologies. We haven't done quite as much review, and really there aren't as many life cycle assessments on the storage technologies, but there's quite a number of references you can see and estimates within those references. Some references have many estimates from different scenarios, and that's why the number is greater in estimates than there is references. But a lot of studies on photovoltaics, and more. We haven't really updated this one very recently, except in the international context, but not from this literature standpoint. But you can see that photovoltaics, along with other renewables in central tendency, 50th percentile is the median, is under 50 grams CO2 equivalent per kilowatt hour, and that's in comparison to the fossil energy sources, which start at just under 500 grams CO2 equivalent per kilowatt hour for natural gas, and staircase up to coal at a benchmark of around 1,000 grams CO2 equivalent per kilowatt hour for unmitigated or unabated coal or natural gas or oil electricity generation. When you do have carbon capture and sequestration, then you can reduce that, and those are the red dots sitting below natural gas and coal. We, in the IEA PVPS Task 12 group that I lead, we maintain and annually or biannually update our assessment for the environmental life cycle assessment of electricity from PV. And so this is a fact sheet that we maintain on this website, and the link is there. A general link to all the publications from Task 12 will be provided in this slide deck. This is more complicated than I need to explain every detail of, but basically we establish a system boundary in life cycle assessments. There are certain things that are inside and certain things that are outside of system boundary. In this case, we're looking at the bottom many different technologies for photovoltaics, which means different materials going into them, different production processes, and different form factors and other differences amongst those technologies. They are transported to where you have the PV system is being installed, and then it's used, and then finally you have an end-of-life scenario for each of those. And so we receive data from industry for some portions of this, and we use other secondary sources for others. These are some of the key parameters. In orange are all the updates that we made most recently. So in particular, we update the module efficiency, but we also pay attention to things like the wafer thickness. The kerf loss refers to the amount of a silicon ingot that is sawed off to get to the wafer. So that's referred to as kerf loss. Sometimes that's collected and reused in the factory, sometimes, most of the time not. And we track any energy consumption, especially electricity, but also any other energy from thermal sources, for instance, in tracking this. Monosilicon, mono-Si, Si standing for silicon, is the dominant technology today. Cadmium telluride is a thin film technology. It's more or less painted onto a glass surface. It's the leading thin film technology. You might have heard of another technology called perovskites, but that's not commercialized yet. So we're talking here about commercial technologies. These are the current, in our assessment, impacts. This is with a European basis, so there'll be some differences to the US, but I argue not very much. Most of the environmental impacts are embodied in the manufacturing, and that's a global market, as opposed to where it is deployed. So just under, well, substantially under, I guess, 40 grams CO2 equivalent per kilowatt hour is the mono SI. That's the 95% of the global market, fluctuating, but approximately 70 to 90% of the US market. Cadmium telluride makes up basically the difference. Its efficiency is a little bit less, but as you'll see, where the efficiency is here in the previous chart, it's a little bit less, but it has lower life cycle greenhouse gas emissions, partly because of how it's manufactured, and also to some degree its end of life scenario. The major manufacturer of cadmium telluride is First Solar, a US-based company. Although it has manufacturing operations overseas, it maintains a recycling center for its own products, and most of the products deployed today have been sold with recycling as a bundled service. The more recent contracts for purchase of cadmium telluride does unbundle the service of recycling from the purchase of the product, but they still do run a recycling center adjacent to their manufacturing centers in the US and globally. These are the components of the life cycle assessment in terms of greenhouse gas emissions, comparison across the four major technologies. Silicon PV is moving ahead, and there are other newer technologies that are gaining market share. We're not representing those here. One is called PERC, and I forget it. Passive emitter, I forget exactly what PERC stands for. But in any case, we do have a life cycle assessment on that new technology. It's not represented here in this sort of global review, if you will. But the components of this, the bulk of the life cycle greenhouse gas emissions come from panel manufacturing, but there are also balance of system components, including the inverter and other balance of system like racking, cabling, etc. You can see that recycling makes a very small contribution at end of life, and the operation is negligible. Can't even really see it in the chart here. This slide I think is very interesting because it shows the time series across our first assessment of the embodied or life cycle greenhouse gas emissions from 1996 for monosilicon PV, and it goes from, now it's almost a quarter of what it was. In 2023, it's at 36 grams CO2 equivalent per kilowatt hour compared to 1996 of 121. So along with the efficiency improvements and the cost improvements of photovoltaics, so has improved the life cycle greenhouse gas emissions of this product, which was already an order of magnitude lower than coal and 20x lower than natural gas, but it's even lower than that now. Often people ask questions around what is the energy payback time. They understand it's an energy intensive process to manufacture PV modules, so when do you pay that back? There have been claims, but those have been debunked, although they seem to resurface every so often, that the modules don't repay themselves in terms of energy produced. That's not true in international assessments, including our own, but not only our own. And in fact, the payback time is about a year for modern PV modules. These are many other publications that we have in this IEA PVPS Task 12. The cluster of 3 on the top left are the life cycle inventories that we maintain so that life cycle analysts can use data that we collect and vet and then publish and maintain. We're producing another update now with as much industry primary data as possible. So you can find that it's in formats that are compatible with LCA software, so it's easy to use. And these life cycle inventories are the basis for international standards, such as the the Global Electronics Council low carbon or ultra low carbon and low carbon PV that is now a standard for the EPEAT program for purchasing. We also maintain guidelines for conducting life cycle assessments of PV. And we'll have another update of that coming up in a year or so. We maintain guidelines on doing the net energy analysis calculations, which is slightly different than life cycle assessments. At the bottom, going to the right, we have 3 in a series of human health risk assessments. They may be relevant. I didn't hear that being discussed in the first presentation, but many stakeholders have questions around some of are there health risks associated with PV modules in different scenarios. The first one we conducted was around PV exposed to fire. The second is around modules that have broken glass but are left in the field where water can wash over them and there is some leaching of materials from within the modules onto soils. And the third is modules if they were to be put into landfills. All of these assessments use or rather follow US EPA and National Research Council, part of the National Academy of Sciences, guidelines for conducting human health risk assessments. Those guidelines say that to do screening level assessments, which is what these are, one should take health protective assumptions at every step along the way, which we do. Those health protective assumptions are extreme in some cases. So for instance, there is for the module disposal risk, that's for landfilling, we assume an unlined landfill. That's illegal in the United States. But nevertheless, it would represent an extreme case, and certainly internationally it might be relevant for certain countries that don't have regulations that require lining of landfills. But even under that that's an example of one of the extreme assumptions we make to be health protective. All 3 of these risk assessments have found that cancer and non-cancer risks are order of magnitude or more lower than US EPA guidelines for cancer and non-cancer risk. In the bottom are 2 examples of our circular economy publications. One is a fact sheet. That's something that would be accessible to the general public. The one on the right is a life cycle assessment that's specifically on a component of a recycling process. Actually, it's the hardest step of the recycling process, which is separating the glass from the layers underneath, either a second glass layer and bifacial modules, or a backsheet in traditionally designed modules that just have one glass surface. So this is a new technology that is manufactured in Japan, but is being used by some recyclers globally, including the US. So to transition to a second part of the talk, I was asked to talk both about life cycle assessment and circular economy. Just to define circular economy, it moves from this linear take, make, waste paradigm to where we have all of these arrows that are going into more circular directions. The circular economy is distinct from a recycling economy. The recycling economy fits well into a linear because all you're doing is focusing on the end of life phase, whereas a circular economy wants to also consider redesign, in this case of PV modules or other components, for repair and then lifetime extension, for reuse either directly or with repair, and then finally at end of life, if there's no more possibility for repair or reuse, then recycling. So this is sort of going over in a little more detail what the fairly standard now 10 R strategies are. So it expands beyond the reduce, reuse, recycle sort of elementary school mantra to all these other categories or strategies within a circular economy, where we're moving from R9 to R0 towards a more circular economy approach. One motivation for looking at the circular economy for photovoltaics is that we're going to have in the future a significant amount of PV modules and other components that have reached end of life. It's happening now. There are modules that get broken before they get installed or during installation process. There are modules that get encounter extreme weather events, hailstorms, hurricanes, and other ones, tornadoes, etc., that could destroy a module and make them unrepairable and unreusable. And those are actually not considered yet in the model that we have developed called PV ICE, PV in the Circular Economy. There's a link to that model in this slide and a report where we used it to look at scenarios in the US supporting the Department of Energy's Solar Futures study. And you can see in blue, in a shade of blue, Maryland, or at least the eastern and central part of Maryland. So relatively more anticipated volume, in this case of glass, one of the major materials, the major material, I should say, by weight within a PV module, not necessarily by value, but by weight. And so Maryland is a state that we have projected to have somewhat greater relative to other states amount of glass. This is a 2050 scenario. And we have in this report all years, or maybe it's every other year, between the publication of this report and 2050. So you can look at the trend of that. This model, I think, is really fantastic. I'm not the developer of this model, but I just love it because at any spatial granularity that you provide input data of the deployed base as well as a projection of deployment of PV modules. So for instance, if you had it by county or if you had it by zip code, which New York State has, you can use this model and you can then predict in the future the anticipated mass of constituent materials, not just the total mass of modules, but the constituent materials within modules, based on the year of manufacture, which is assumed to be the year of installation of the module, and the ingredient list, a standard ingredient list that we've put together in time series for each of those vintage years. And so we account for changes in glass thickness, changes in wafer thickness for silicon, et cetera, all throughout those years to provide as accurate as possible a future forecast of the amount of materials, which you then could apply a material value to estimate the potential value, if fully recovered, of all of those materials in your modules. And done at a global level, looking out just at 2050, this is from now a while ago, 2016, and there's going to be an update published actually very soon from the International Renewable Energy Agency, a sort of sister agency to the one that I do a lot of work with, although I was a co-author of this particular publication. We anticipated up to 80 million metric tons of end-of-life PV mass, module mass, I should say, in 2050. And that would create about 15 billion US dollars in value from the potentially recovered materials. Now, things have changed since 2016. In particular, the deployment forecasts have changed considerably, gone up considerably. So we would anticipate by 2050 even more materials available and more value in those materials, as well as new employment and industrial opportunities to harvest those materials. One point that's often of interest to especially state and local jurisdictions is jobs. And I really like this quote from Waste Management Incorporated that recycling creates more than 10 jobs for every 1 job created by landfilling. So there's a lot more job creation possibility in recycling than there is from landfilling. And so it's also an opportunity to participate in the clean energy economy, which has a much higher value, sort of personal value, I guess you could say, for those workers, and it requires higher skills, for instance, repair and even recycling versus landfilling. We have just very recently, just May, published an assessment including primary data collected from 7 recyclers around the world, including US recyclers, for their life cycle inventory. So the amount of energy that's used in recycling process and the materials that are recovered. And on the right is an example of a process that's used by a German company And it's just an example of one. We have that same kind of process flow for all the recyclers that we partnered with to collect their data and publish through this report. On the left, the chart on the left shows 2 commercial operations and the amount or the fraction of materials that are recovered in terms of total mass that's recovered from these. And the main difference between the cadmium telluride and the crystalline silicon commercial operation is that the module is designed differently. So you have a different amount of materials that you're going to recover of each of the material types. All the other processes that we collected data from are pilot scale, so they're not full scale, and they're actually all the other ones are European, but nevertheless they are important benchmarks for us to be aware of around what does it take to recycle and what can you get out of it. Tracking electricity consumption, the plot on the right, is very important because that's really the main energy input and therefore environmental input for the recycling operations. Lots of different processes are used in these recycling operations, from mechanical to thermal to chemical or combinations therein. Mechanical processes are really the only ones that are fully commercial, and they set a benchmark for maturity cost and low energy consumption. The riling system is the example of that. And that was hopefully covering some of the information that you all hoped to hear, and I'm happy to take any questions, have some discussion around this. There were links provided in the presentation, and you're welcome to use those. I think that these slides were going to be posted for all attendees.
Yeah, and depending on how fast our website updates, they may already be posted. And I think it does take a day for it to show up. Well, thanks for that. I did actually have a question. So the statistic about the 10-to-1 jobs, was that waste management specific, or was that something that was being cited from a study, or do you know?
I did try to query a little more about this, and it seems to be coming from the experience of this individual who works at Waste Management, Inc.
Oh, I see. Okay. All right. That's it. Thank you. Are there any other questions for Calvin? Bob?
Yeah, thanks. So, great presentation. I like all the data. So it looks like you have a really great model. So, but you talked about lifetime greenhouse gas emissions or total emissions going down for solar over the time series that you had. Can you explain that? Why that is? Exactly. Yeah.
Sure. One of the main factors that accounts for this is the module efficiency, which is also shown in this chart. So you can see the middle row shows the module efficiencies starting in 1996 at 13.6 and going to almost 21% in 2023. This is the commercially deployed average. It is not the sort of leading edge research-based module efficiencies that are announced by different research group, and NREL also tracks. This is what's being deployed. So the ones that are being manufactured at commercial scale and being deployed. So when you have greater module efficiency, you are producing more electricity. So the metric life cycle greenhouse gas emissions is lifetime greenhouse gas emissions from all the phases of the life cycle. Again, pointing back to this diagram, upstream, operation, and downstream being summed into that total. And then divided by the lifetime electricity production. And so when you have the same, if you have the same embodied, let's just say you have 2 modules that have the same embodied materials in them. They have the same weight, they have the same weight fraction of glass, silicon, plastics, other metals, etc. But one has higher efficiency than another. That means that second one is going to produce more electricity. And so in the denominator, when you divide by a greater number, you get a lower gram CO2 equivalent per kilowatt hour. So therefore, over this time period, 1996 to 2023, by increasing the module efficiency by 7 percentage points, which is 50% greater than the 1996 value, you're going to reduce, all other things equal, you're going to reduce your life cycle greenhouse gas emissions by that approximately 50%. Now, there are other changes going on as well. And so that's the reason why I showed what we track as the key parameters of wafer thickness. Silicon is the most energy intensive material that's going into a PV module, because it's the purest one. So there's a lot of process that has to go into making that pure. In fact, silicon is the most pure substance, man-made substance on Earth ever. And silicon that goes into PV modules is now being demanded up to 11 to 13 N. That means 11 to 13 nines, 99.99999, all the way to 11 nines or 13 nines. That's really pure. Purest substance on Earth. And to get there, it takes a lot of energy. So when you have wafer thickness also going down over these years that we tracked, you're also going to have reduced embodied energy content, which is a major factor in the life cycle greenhouse gas emissions for photovoltaics. And those are two examples, but there are other changes in material composition, and you can see annual yield. So they're reducing other losses, and so they're getting more kilowatt hours for every installed kilowatt peak. So the kilowatt is a capacity, kilowatt hours is generation. So if you get more generation for the same capacity, like for module efficiency, you're going to also improve the amount of electricity you produce. That's the denominator. In term, that's dividing by the total greenhouse gas emissions over the life cycle.
No, great, thank you. No.
We also had a question in the chat. Have you seen a base number of units to recycle to make a recycling operation business viable on an annual basis? Thinking of economic development.
Sorry, I wasn't able to quite follow the beginning of that. Do you mind starting again?
Yes, or maybe Andrew, if you want to chime in, if Andrew's still on the line.
I am still here. Yeah, so my question was, from an economic development standpoint, is there a base number of panels that you see a recycling business needing to have on an annual basis in order to be viable?
I'm sorry, I don't have a rule of thumb for that. The recycling, but I can give you a few comments that might give you some insight, although I don't think it's going to get you to a certain number. So the comments are that recycling, like waste management in general, is a low margin business. So you need to have high volume in order to make revenue. And profit is revenue minus cost. So you need to have enough revenue to offset all of your costs. Recycling is also a capital intensive business, so the costs are relatively high, which then skews recycling facilities, especially new ones that would be purpose built, to a relatively large scale before they become profitable. And of course, firms are not going to go into this business unless they can see a path to profitability. There are relatively few in the world dedicated PV recyclers. Most recyclers that are in commercial operation today are existing recyclers that have the know-how to especially deal with certain materials in a PV module. For instance, glass recyclers will look at a PV module and say, hey, this is more than 80% by weight glass. I know how to deal with glass. I'll take PV modules and recycle PV modules. Well, you can easily recycle the frame also. That's metal. That's going to give you some additional revenue. But what do you do with the rest? That's been a challenge still. A metal recycler might look at, the metals, in particular the frame, but also some of the internal metals, and say, hey, I know how to get metals out. I'm going to do that. And the glass, not sure what to do with. The silicon, not sure what to do with. The plastics, but I know how to get the metal. That's where most of the material value is in a PV module. So they have different perspectives on what they can do with a module. So even in the US today, we have existing recyclers who are collecting and recycling PV modules. They tend to have equipment and a business focus that's on their traditional commodity and less on the whole of the PV module and everything in it. Now that's changing, that's evolving both because of industrial investment in R&D as well as governmental and sort of research investment in R&D, and that is advancing. There's no consolidated sort of view from researchers or the industry as to which process is going to be the one that wins out, and which is the best, which do I want to replicate. So we're doing a lot of experimentation now. There is one large-scale dedicated PV recycler in the U.S. It's called Solar Cycle. It is probably the highest invested. So there's they've announced a lot of investments into this. So highest capitalized, I guess I should say, and it is dedicated to PV recycling. There are others that have become dedicated to PV recycling. They're a bit smaller than Solar Cycle, but there are plenty of others out there. You can find a list of, or a subset of the list of existing PV recyclers in the U.S. on the website for the Solar Energy Industry Association, SEIA, SEIA. They run a sort of certification, if you will, program for PV recyclers, and they have several on their website that have paid some dues to become a member of SEIA and to go through a vetting process that SEIA runs. And there are several, including Solar Cycle, but also others that have gone through that process. There is also, and I'm sort of going on here beyond your question, but it might be of interest. There is also a new PV recycling, specific PV recycling standard under the R2 program, Responsible Recycling, that came out of the EPA and is run by SERI, SERI. And the R2 program now has an appendix that's specific to PV modules. I helped to develop it with many other experts, and of course the SERI organization. But that's now available, and I forget exactly the schedule they're on, but I think it's several months still before the first one can be certified. And then finally, I'll just mention again that there is a purchasing standard for sustainable PV. It's called the Sustainability Leadership Standard for Photovoltaic Modules and Inverters. It was originally an ANSI standard, American National Standards Institute, but now it's incorporated into the Global Electronics Council, GEC, the organization that runs EPEAT. And so that provides a way for product specifiers, for purchasers, to not have to figure out how am I going to specify to get more sustainable PV. All they have to do is point to the standard and say, I want to have bronze, silver, or gold labeled PV modules. There are at least 2 manufacturers that have modules that have been certified to this standard that are on their website now, and I understand several more are near completion or in the process of getting certified for that. So if you're interested on purchasing side, you can get low carbon PV, you can get PV that has from a manufacturer recycling process that's being offered by the manufacturer, and some other end-of-life associated points within that point system to get to the certification level, as well as many other aspects of sustainability. I also helped develop those standards.
Excellent. Hey, thank you. That was wonderful. Appreciate that.
Yeah, and you actually just did a rundown of our speaker series in that last answer. So we actually had FDIA speak in a previous meeting.
Oh, great.
And then we're also going to be having SERI and Solar Cycle, and
Yeah.
maybe Solar Cycle Financer give a presentation.
Oh,
And
there you go. Great.
so maybe that's good validation that we were kind of thinking in the right path and all that.
Yeah, yeah. Well, you can also, whoever asked it, asked the question about sort of minimum viability for number of modules or throughput, of modules to Solar Cycle, about what their sort of view on that is.
Yeah. I did have one more question, and then we might have to move on. The slide that you had where you were talking about the central tendency and the distribution. So I just had a question on why the data for the renewable energy is so skewed. Is that because the technology is scaling and getting better at the same time, or are there other explanations for that?
So by skewed, do you mean that there's a greater sort of height between
Yeah.
the
Your third quartile or your top
yeah,
quartile is pretty
yeah.
large, yeah.
Yeah. Well, for every technology except for biopower, there's nothing below zero. So it's common in sort of natural systems that exist in the real world that when you get close to zero, you're going to have skew because there's nothing below zero. So that's just a sort of you'd expect to see that actually, and I will comment again that the last time we reviewed the LCA literature for photovoltaics was a decade ago. So I would expect that we systematic review. That process involves screening of publications. In our case, we establish objective screening criteria for quality of the LCA conducted, for transparency of the results and the methods reported, and for relevance of the technology. If we were to do another review of the literature for photovoltaics, I would guess, this is speculation, but I would guess that many of those values that are sitting up over 200 and even over 100 would probably not be relevant anymore because they were older technologies and they represent a very different manufacturing process than is used today. So my guess is that if we were to do this again, which I hope we will have a chance to, but we need to have funding to do so, if we were to do that again, then I think that you would see that top end drop considerably. And I don't think that that's specific necessarily to PV. I think that would happen for concentrating solar. I think that would happen also for geothermal, et cetera. I mean, all of these that were literature review done a decade ago, there are technology improvements and that would change the distribution.
All right, and then there's just a comment from Scott. Scott, I'll let you chime in and talk about that.
Yeah, sure. I was just mentioning, and this may be what Garvin was referencing, because I know he knows Evelyn Butler really well, but SIA is actually working on these ANSI standards around decommissioning. And so I was just noting
Right.
the 3 standards that are going to be developed over the next few years. One is 601, which has to do with solar and energy storage equipment decommissioning standards. One is SIA 602, which will be solar equipment minimum requirements for recyclers. And then SIA 603, which will be solar equipment end of performance end of life management standards. So those are obviously not finalized, but are obviously of relevance to this group.
Yeah. As far as I'm aware, none of those 3 have started, and I think they're doing staggered starts. So not all of them each one of them will not start at the same time. There'll be one that starts first, and then they'll sort of go through the rest. But yes, I think these are going to be valuable processes, and NREL experts will participate in each of those 3. At least one of us participate in each of those 3, and along with many other experts, and hopefully they will be. For instance, the one you might be scratching your head, why is SIA doing a recycling standard if R2 already has one? I think they aim to make that complementary, so it's not going to deal with the same things that the R2 standard deals with.
And I do have to cut us off, but it's fascinating conversation. And if you have any further questions for Garvin Heath, you can certainly send them an email. But again, thanks so much for the presentation.
You're welcome. I'll put a couple links in the chat, and then I'm going to have to scoot because I'm at the airport. I got to catch a plane. But yeah, thanks for the invitation. Glad you all have convened such a great speaker series.
All right. Without further ado, I'm going to turn it over to the university to give an update on the report that they're helping us to write. And yeah, I'll turn it over to Kathleen.
Thanks. So Bradley with CGS, would you go ahead and share the slides? So both presentations actually are really great lead-in to this study update. So I'm glad we're going last here. As a reminder, our research team is a partnership between CGS at University of Maryland and some folks from Johns Hopkins in the School of Engineering. So we have both teams on the call today to answer any questions. But we'll get started. Can you put the slides on full screen, Bradley?
Sorry, give me a second.
No problem.
Can you see them?
Yes. Okay. So first, we're going to start today with a bit of a profile of current solar installations in Maryland. Then we'll take a look at the different end-of-life options, which Garvin just queued up really well, specifically the options that exist within a PV circular economy framework. We'll provide some examples of policies that might lead to a circular economy, as well as the financing approaches that could incentivize one. And then we are using the PV ICE model that Garvin also mentioned in his slides. So we'll provide a bit more of an overview of that model and a look at the scenarios that we're planning to use. And then we'll end with a look at the state of landfill capacity in Maryland and how that might relate to solar deployment in future and some next steps for the study. So first here we see solar currently in Maryland, and you can see this graph of installations over time. Historically, the majority of solar installations have been residential. They're in the dark blue. The utility scale solar installations are in the lighter blue up top. And so you can see in more recent years, they have started to expand a bit more. And then just in 2023, particularly, there's a large increase in community solar installations. But the current capacity is around 2,000 megawatts, and SEIA does expect growth over the next 5 years with another additional 2,300 megawatts. But as Bob mentioned in his slides as well, there is more still needed to meet Maryland's RPS goals of 14.5% electricity coming from solar. So based on modeling from the Climate Pollution Reduction Plan, we would estimate this just under 4,000 megawatts needed by 2030. And finally here, we've got this table in the bottom that is specifically for solar installations that are greater than 1 megawatt. So this is the more utility scale. And we've got a breakdown of the material types. So the majority is crystalline silicon. And then there's just a little bit of CadTel. There are 2 installations specifically that make up the majority of the remainder. Next slide. So specifically for those larger utility scale installations, we've got a map here showing where all of those are located within the state and when they were installed and the capacity of those installations. So you'll see the darker colored dots indicate older arrays and the lighter colored yellow dots indicate newer arrays. And so a couple of the larger ones are out on the Eastern Shore. And there's very few installations in Western Maryland, and those that are there are much smaller. The histogram that you see here on the bottom left is showing that the vast majority of the arrays in Maryland are on the small side, so most below 20 megawatts, and then just a few on the larger scale. And we also have data on the next slide about the type of installation that each of these was built on. So the majority were greenfield installations on a new site. There are a few on landfills. You see those in the brown, and one on a Superfund site in black. There are also 2 agrivoltaic installations in Maryland, one over on the Eastern Shore and one in Howard County that you can see in the square instead of the circular dots. So that's a quick overview of the current installations in Maryland. And now I'm going to turn it over to Stephanie to kick off the next steps on looking at what might be done with these solar installations at end of life.
Kathleen, so this is another slide about circular economy, and Garvin gave a great overview of what that is. These are just different visuals on how We can visualize the circular economy as well as the waste hierarchy on the right side of this screen. We just want to emphasize that we are following a circular economy approach that is in line with what Garvin presented. And I think with this framework, this working group and the study can really consider a full spectrum of policies in managing the materials within solar PV systems, not just thinking about recycling, but also higher up in the value chain, as Garvin mentioned about how we design products to last longer or use less materials. So yeah, I think that's the biggest takeaway for this slide, and then I'll pass it on to Bradley to talk more in depth about some other things of the study.
Yeah, so keeping that framework in mind, we started to look at the literature to see where else folks have done a deeper dive into these circular economy considerations for solar. And so I'm looking at one National Renewable Energy Laboratory report. They actually did a simplified cash flow analysis of different end-of-life options for a kind of 1 gigawatt idealized utility scale solar plant. So these graphs are kind of very basic cash flow graphs that indicate, the initial capital cost of the solar plant, as well as ongoing operation and maintenance costs, as well as other common costs in there like tax credits, as well as the decommissioning costs. And so the general takeaway from this is to show that some of these other circular economy approaches can have some economic gains in showing a lower overall project cost or lower cost of electricity. It's important to note that these graphs don't show, let's say, the revenue side. It's mostly the cost. The only sort of quote unquote revenue you're going to see here is from tax credits and other related tax implications. But as we can see in the top left, in our base case, we have a decommissioned plant that after 25 years is decommissioned. The green line that slopes downward is the energy delivery. And so we presume about 1% degradation over the project lifetime in terms of how much power is being delivered by those solar panels. In the extend case to the right, the overall cost goes down because we leave those panels in place. And so we defer that decommissioning cost to later into the future. And we're continuing to see decreases in power output. And so our, the amount of power coming out of this plant is less, but given that deferred cost, the overall levelized cost of electricity, again, this is simplified in the scenario, it's a little bit less. In the refurbish and repower case, we make some assumptions around refurbish. We're basically saying, okay, the way NREL sees it is reset the recoverable degradation rate, but what that means is basically repairing, refurbishing the panels that can be repaired, right? So some degradation is repairable on these panels. And in doing that, we incur another relatively large capital cost when we refurbish them in year 25. And as a result, we now have more power output in our plant. And so that's why that energy delivery green line kind of resets. And then in the repower case, we incur a larger capital cost because we basically presume to replace all the panels that no longer give us the power output we want. And as such, we kind of reset the energy delivery, incur a higher capital cost in that 25-year mark, but the lifetime of the project is much longer. And so we're still kind of utilizing some of those balance of systems components that already exist in that solar installation. So the key takeaways here are that end of life cost, that decommissioning cost is 10-ish% or so of the total LCOE. Again, this is a simplified, idealized version. And it's important to note that some of these circular economy, such as repowering and extending these project lifetimes, can actually lead to lower costs overall of the project. And so kind of leads us into thinking more broadly about financing of recycling. And when we did a policy review, we see it kind of taking, broke it down in kind of these 4 different categories. So one, you can imagine a very simple fee-based system where when you install a panel, whether that's in utility scale or residential, you establish a fee that's associated specifically with recycling or some other end-of-life treatment. Interestingly, that was part of previous Maryland legislation that was proposed that I'll talk later about.
Another common policy mechanism is extended producer responsibility, which I'm sure this work group has heard about. I'm sure you've heard about the Washington State EPR program, but the EU and South Korea also have EPR programs. This is where the onus and the responsibility is on producers, manufacturers, and in some cases sellers, those that lease them or install them, on the end of life disposal and costs. Others take more regulatory approaches, such as a universal waste designation, with the idea that it gives clarity to the handling of those end-of-life panels, and therefore will help reduce the cost of transporting and storing and handling that waste. It doesn't explicitly do anything necessarily to increase recycling, but it is something that has been done specifically in California and elsewhere. And the EPA is doing rulemaking, as we heard in the last meeting, regarding a universal waste designation for panels. Another kind of common regulatory action we'll see is a landfill ban or a landfill diversion policy. And this would work by fees or fines or other penalties imposed on those who do end up dumping PV in landfills. And it would seem that the purpose here is to induce some kind of market generated solution for end of life panels that isn't necessarily dictated by policy, but is dictated by the need to create a market or something like that, because you cannot put panels in the landfills. And North Carolina has, and others have explored that option. So as I mentioned, I'm sure you've heard about these extended producer responsibility programs. Obviously, they apply to other things such as electronics and whatnot. But I wanted to talk about some of the different legislation proposed in other states to show you kind of the whole solution matrix of what an EPR program could look like, right? So in some cases, like New York, they explicitly outline in the language of the proposed legislation that fees cannot be charged to consumers. That's a pretty central tenet of EPR programs. They also include language for education, outreach, and communication, so that consumers are aware of this program. Arizona kind of expands their definition of who's covered under here to include those that sell, lease, and manufacture panels. So in some cases, people just in these proposed legislation include manufacturers, others expand it. And like in Arizona, they included this provision for landfill diversions. Sometimes these things are paired. There was a similar case in Minnesota. There, they also include language about reducing waste generation in general and promoting recycling. And then, as is common, many of these pieces of legislation, Rhode Island, with language about having plans submitted to their state government, and also include language in which manufacturers could designate outside stewardship organizations to handle the end of life of solar panels. So in some of these programs, the manufacturers or sellers themselves may not have the infrastructure, the logistics to handle panels at the end of their life, but they can designate outside organizations to handle that for them, and they will submit plans to the state governments to review them and whatnot. There are other states that are completed very similar processes to what this working group is going through right now. And they also definitely looked at and made recommendations around circular economy. So in North Carolina, they really seem to push for observing pretty strictly that waste hierarchy that Stephanie touched on earlier, as well as Garvin Heath touched on earlier, that pushing for panels to only be considered end of life when they really are no longer functioning or when their power output really, really drops a lot. They focused a little bit more on utility scale plants, speaking to what Bob spoke of earlier, which is ensuring that these kinds of end of life costs are considered very much upfront in those decommissioning plans. And they also, there was a bill proposed in North Carolina around panels from utility scale plants, first trying to be recycled and reused before just strictly going to a landfill or some other end of life treatment. In New Jersey, you could see a similar theme of some language around keeping these utility scale plants in place, even beyond kind of the typical 80% power output that is kind of a benchmark for potentially considering end of life. They also have recommendations around trying to create secondary markets so that maybe some of these panels that do hit below that 80% power output, which are still functional but at a lower power output, could be used in underserved communities or other communities in which they may not have the same level of financing to purchase and install solar panels. They also make suggestions to kind of follow one or two of these pretty common tracks around solar recycling policy around universal waste or an EPR program. So that's kind of an overview of what other states are doing. I do want to bring up previous Maryland legislative efforts around recycling. So for 3 years in a row, starting in 2018, there was a bill. It may had slight differences year to year, but mainly focused on creating PV recycling fees that would feed into a PV recycling fund. Those fees would happen at the point of installation and would also happen at the point of the first REC sale, the renewable energy credit sale. The way it kind of operated is shown in this diagram in the center, where these fees are collected into this PV recycling fund, which would then go in general to fund recycling at large in the state. So processes and technologies that assist with recycling in Maryland. Importantly, what the fiscal and policy notes highlighted in these bills is that local governments, as part of this legislation, could not impose other fees to solar installations. So this could have impacts for local revenue. But overall, these bills were slated to be cost neutral to the state in terms of government financing program itself. But just want to highlight, none of these programs in particular made it out of committee. In 2020, there was a EPR-like bill in which there was a bill proposed in 2020 that also didn't make it out of committee that would have directed Maryland Department of Environment to create a stewardship program and create guidelines for that then they would then implement to manufacturers and others in the state. It also included provisions around establishing reuse and recycling goals, which is actually similar to the Washington State EPR program, which also has reuse and recycling goals. Just to highlight again, these bills did not make it out of committee. So moving on from the kind of policy review to the actual modeling we're going to do. So in partnership with Johns Hopkins University, we're using the PV-ICE model to look at the waste and materials and module level waste generated from different levels of PV deployment. So the PV-ICE model allows for the evaluation of these different end-of-life options and the impact on waste streams. And just a reminder, we saw similar information earlier about what makes up a PV module shown in the left. And so the items in green on the left are bulk materials and also materials that have recycling streams right now. The other notes, the other colors designate semi-high value or high value materials that are in much smaller amounts in the modules, but it could be of high value if they're are able to be extracted through recycling. For example, silver can be high value material. And this model, we're going to be able to adjust the baseline parameters to really reflect the current state of technology as well as the current state of deployment in Maryland. As of right now, we're making an assumption that most future deployment of solar in Maryland is crystalline silicon modules. And part of that is because since we are focused on solar end of life, any change in technology that happens, say, in the next 5 years, that won't start to be decommissioned in large amounts until 2050, perhaps, maybe some before that, but not a lot before mid-century. So getting into exactly how this model works, we have some of our basic modeling inputs on the left are recycling rates, reuse rates, as well as what we designate exactly as end of life, as well as degradation rates. And so those feed into the simplified model that are shown in the middle here, where we have a set of materials that are extracted that go into manufacturing that turns into installed capacity. And from that installed capacity, we either have end-of-life panels, or we can actually take panels in the model before they reach end of life and reuse or repair them that turn into install capacity right then and there. But in that group of modules that reach end of life, we have different options. We can resell them from an end of life market. We can remanufacture them. So you can, in the model, this might mean taking one of the glass portions of the panel and directly using that for remanufacturing, or we can recycle and turn many of those materials into raw materials for manufacturing again. And the main model output that we're interested in here is the waste generated and the material waste generated from these different scenarios. So in considering what we can model, we have a kind of a scenario matrix here that we're looking for more feedback on from the working group. And so it kind of cuts along two different dimensions. One is deployment level, where we have three different situations. One of them we'll call the business as usual, where we're using the existing deployment rates from the EIA data, the current solar deployment, and kind of carry that forward. The next one uses the current policy scenario where we follow that RPS target, that's that RPS solar target of 14.5%, Kathleen mentioned earlier. And then we scale that forward using climate pollution reduction plan modeling. We also have the current plus plan policy scenario where we presume a higher level of solar deployment that would be seen in the Clean Power Standard. And again, taking that from modeling to carry that deployment level forward. So we have those three levels of deployment, and then we cross that with these different end-of-life approaches. And again, this is where we would love more feedback about people's thoughts of what should be modeled here. So we'll have a no policy case where we just presume that all the waste generated is landfilled. We'll take kind of a mimic an EU EPR policy case where we have these recycling targets that phase in different years of 80% of materials by weight recycled, and then 85% in a later year. And then we'll also have a circular economy scenario in which we take a percentage of the waste stream and presume that it can be repaired or remanufactured, and then also make an assumption about how much can be reused, and then make a recycling mandate for the remainder of the panels. So considering the three levels of the deployment and then the three kind of stylized options for end-of-life policy approaches, we'll end up with 9 total scenarios. And again, we'd love any feedback that folks have on creating this scenario matrix. In terms of, thinking about how our inputs, we actually model our scenarios, giving the inputs. You mentioned we could set the parameter for when a panel reaches end of life. We can change that kind of nominal 80% number that is pretty common out there of, panels end of life when it's reached below 80% of its nameplate capacity power output. We can change levels of future deployment, and then we scaling recycling rates, as I mentioned. The knobs we can turn with regarding to circular economy, not only reuse and repair, but also stay in place parameters to reflect that idea that we saw in North Carolina and New Jersey of keeping panels in place longer, even if their power is dropping over time. And I include these definitions below of repair and remanufacture, just so that we're clear about in the model how these are being modeled. It's the idea that being repair is, something that's prematurely failing in the field, but we can return it to the field, the initial installation, and it keeps generating power. Remanufacturing is, taking those panels, pulling off the pieces that we can then put back into that manufacturing string, like those glass sheets, and put them back on new panels. So in thinking about potential model results we anticipate seeing, some natural questions and implications that follow from that are, this need for remanufacturing and recycling facilities. And David Combs kind of spoke to this earlier, that folks at University of Maryland Global Campus, capstone class there, or a class there, has been thinking about in greater detail locations of these recycling facilities and the features they need to have. Concerns for transport of new and used panels for resale and remanufacture will come out of this as well. There also needs to be consideration of secondary markets as well as others in this working group I spoke to earlier, the need for recertification standards, and this standard was brought up in an earlier presentation, but standards are being developed for recycling, but also for recertifying so that folks know on the secondary market that the panels they're getting have some power output that is worthwhile. And the last impact, of course, is on landfills, and that will jump into that right now. And so we're taking just a brief look right now at landfills in the state. And figure 1 on the top right here shows the total kind of waste managed by Maryland permitted facilities. And this graph was taken from the MDE Lands Administration report on waste from 2023, but reflecting calendar year 2022. So we're seeing recently around 9 million tons of waste being managed. And when we think of that number in the context of other results we've seen from EPA presentation at this working group about a month ago, in kind of the worst case or the early loss scenarios in 2040 and 2050, we see about 100,000 tons and then 237,000 tons of PV specific waste in those years. So just want to bring up those numbers for kind of an order of magnitude. And the questions that naturally arise from here is that, how many landfills in the state actually accept solar panels? Let's say one solar array was decommissioned and the panels were to be landfilled. Would landfills in the state take them? Is there a possibility as a result that waste gets shipped outside of Maryland for disposal? And other questions around if solar panels could potentially be tied to a covered electronics recycling program, because covered electronics is a program that is e-cycling is something that's happening in Maryland. The amount of e-cycling is definitely smaller than these potential PV waste estimates, but again, these are preliminary numbers. And so looking at where these landfills are in Maryland, and we started to do some outreach actually to county recycling coordinators, kind of asking some of these questions if they would recycle, if they would take PV waste. So far, we've actually gotten about 7 responses. I just got a response in the last hour or so. Many commented that they maybe wouldn't take large amounts of panels. Some say they wouldn't take any. Some said they've taken a few already, or they would take a few. Many of them don't have county level guidance exactly on solar recycling and or other end of life processes. And a few mentioned potentially waiting on MDE guidance. And this map on the bottom shows kind of the distribution of operational landfills or open landfills, I should say, in the state, with the larger ones representing a higher remaining capacity and the darker colored ones with a closure year that is near closer to now, and versus the yellow or lighter dots representing closure years that is much further into the future. An important note here is that, there's a data lag here. So there's potentially more capacity that isn't fully mapped here just due to this data lag. And so as kind of mentioned earlier, one thing to also keep in mind with this landfilling question is just that the solar PV waste stream is going to change over time, right? So a lot of it now is just going to be manufacturing defective panels or panels that get damaged in transport or installation. Whereas, in 2037, as Bob showed in his graph earlier, many more are actually going to really reach their end of life, or whatever the end of life for that given solar plant project is. And with that, I'll turn it back to Kathleen.
Thanks, Bradley. So I wanted to end with a couple thoughts on next steps for this work. So once we have finalized these modeled scenarios and gotten our results there, we're planning to use the excellent work by Garvin and others on life cycle assessment to analyze the potential impacts of the waste stream. So we can utilize these existing LCAs to think about environmental impacts, the impacts on GHGs, et cetera, and we'll provide comparisons with other technologies whenever the data is available. I know sometimes we have really excellent data like this for the GHGs, and others there may not be a good comparison across different technologies. So we'll do as much as we can of that. And we'll also follow up with more outreach to the counties and solar installers or developers to bring in their perspective to this work. So with that, I'll open up for any feedback or questions, and you can see our contact info on this slide if you want to follow up after the working group meeting as well.
Any questions for the group? All right. Well, hearing none, I want to open, let's just go to the agenda. So the next part of our agenda is QA and member discussion, to talk through some of the things that we saw today, if there's anything else that you want to bring up, and then we will end with public comment. So opening the floor up. These must have been some pretty good, thorough presentations. So thank you to all the presenters. I know I'm definitely feeling charged up after all those presentations. Now I'm going to move on to the next item of our agenda, public comment. Is there anyone in the public that has something that they want to comment on? All right. Hearing none, I think we are good to adjourn. Again, thanks so much for joining us. We have another meeting scheduled, I believe, in September, and more information to come on that. All right. Thank you. Talk to you all later.
Thank you all.
Thank you.
Thanks, brother. See you.